This video is the second half of the examples on NullSpace and NullVectors. It involves example 10.5.6 of the book, revisited in the language of the NullSpace and NullVectors. So we will not be thinking about the inhomogeneous part of the matrix in this round. So if I look at the original matrix A for this problem, it is 1 minus 1, 1, 3, 0, 2, 1, 0, 3, 3 minus 1, 6, 2 minus 1, 2, 1 minus 1, 7, 1, 0, 5, 8 minus 1, 7. Okay, so after we do Gaussian elimination, that matrix is row equivalent to 1, 0, 0, minus 9 halves, minus 1, 9 halves. Then the next row is 1, 0, 3. I'm sorry, 0, 1, 0, minus 5, minus 1, 3. The next row is 0, 0, 1, 5 halves, 0, 1 half. And the final row is trivial. Okay, so if we think in terms of our leading ones, we have only 3. So this is to be contrasted with the last example where we had 4 leading ones, 1 for each of our rows. So since we have the last row with no entries remaining, we're missing a leading one, and so instead of having 4 leading ones and 2 free columns, we only have 3 leading ones, and we have 3 free columns. So this matrix is called rank deficient. So this is rank deficient. And so the rank, which could have been 4, is only 3. So the rank is 3, which means that the dimension of the null space, which we knew had to be at least 2, is actually 3. We have one extra null vector. So dimension of the null space of A, we knew it had to be at least 2. It actually turns out to be 3 because we had a missing leading one and one extra free column. So there are 3 free columns. We knew there had to be at least 2. Okay, then how do we go about defining our 3 null vectors? Well, we just write the solution to the homogeneous equation. And so let's say that x 6, that corresponds to a free column. Let's call it alpha 1. X 5 corresponds to a free column. We'll call that alpha 2. And x 4 corresponds to a free column. We'll call it alpha 3. Okay, now we have 3 more equations to determine x3, x2, and x1 in terms of alpha 1, alpha 2, and alpha 3. So our third equation says that x3 has to be equal to negative 5 halves alpha 3 plus 0 alpha 2 plus 1 half alpha 1. That's all negative. The next equation, equation number 2, says that x2 has to be equal to negative, then I have negative 5 alpha 3 minus 1 alpha 2 plus 3 alpha 1. And then my first equation for x1 tells me that x1 has to be equal to negative, then I have a negative 9 halves negative 9 halves alpha 1, sorry, alpha 3, plus 1 times alpha 2, plus 9 halves times alpha 1. Okay, so now we have our 3 null vectors. Null vector number 1, x homo 1, corresponds to alpha 1 turned on and the other is turned off. So alpha 1 is equal to 1, alpha 2 equals 0, alpha 3 is equal to 0. So if I just write my values for x1, x2, x3, x4, x5, x6, for alpha 1 turned on, this is going to be negative 9/2. That's this slot right there. Then for the number 2 slot, I have a -3. For the number 3 slot, I have a -1/2. For the number 4 slot, I'm going to have 0, 0, and 1. So this is our first null vector. Our next null vector, x homo 2, which is going to be alpha 2 turned on, and alpha 1 and alpha 3 turned off. So I have a -1 in the first slot. In the second slot, I have a negative times a negative, that's a +1. In the third slot, it corresponds to this equation right here. I have nothing because of my 0 in the alpha 2 slot. And then I have 0, 1, 0 for the remaining 3. 0, 1, 0. And I'm sorry, I have a sign error on this guy. I'm sorry, in my row reduced form, that's right. Bear with me, there may be a typo in the book. And then finally, for my x homo 3, which is for the alpha 1 turned off, alpha 2 turned off, alpha 3 turned on. If I look at x1, that's going to be negative 9/2. That's going to be positive 9/2. If I look at x2, that's going to be negative 5. That's going to be a positive 5. If I look at x3, it's going to be a negative 5/2. If I look at x4, by definition, that's going to be 1, 0, 0, because only alpha 3 is turned on. So that's my third null vector. And so if we multiply any one of these on the left by a, we should get the 0 quadruplet as a result. And these three are linearly independent, which means they make a basis for the null space.